All right, and we are about to start the most useless section in the class, which is called curve sketching. I think this was very popular when we didn't have a lot of technology, but at this point in the class, well, it's kind of useless with all the technology we have, but it is in the syllabus, so we do have to know how to do it, which is slightly stupid, but we'll get through it. All right, so what this section is about is pretend you didn't have your graphing calculator, and pretend you didn't have a computer, and pretend you didn't have anything that can draw a graph of something. We actually can take all the information that we've done so far and figure out how to graph the curve. All right, so that's basically what this section is about. We've pretty much done all the work into like figuring out what to do for all of these questions, but putting it together and creating the graph is like the last kind of step in this. So what we're going to do today is just answer a few questions about this weird graph or this weird function here. And we're going to use all the information that we have to finally figure out what it looks like. Okay. All right, so this is a function. It has a denominator, which means it's a rational function, right? Which means it can be expressed as a fraction. And taking a look at this equation here, how would I find the domain? It's going back to like the very first thing we did in class. Yeah, look at the denominator, right? Whenever we have a denominator in our function, the denominator can't be zero, right? Because if we divide by zero, then, well, that wouldn't work. So normally when we find the domain, the first thing that we do is we take the denominator and we set it equal to zero, right? And then we basically solve for x, right? So taking a look at the denominator, x squared minus 1 is equal to 0. Okay. Once we do that, guess I can add 1 on both sides. So x squared equals 1. And taking the square root of both sides, we have x equals the square root of 1. What am I forgetting when I take the square root? Plus or minus, good. So x is equal to plus and minus 1. Okay, so it looks like my x values can be anything except for -1 and +1, right? Writing this in interval notation, well, first I can kind of graph what my intervals look like. I have -1, I have 1, and my graph can, or my x values can be anything except those values. So literally I have 3 intervals, right? I've got -infinity to -1. I've got -1 to 1, and I also have 1 to +infinity. Okay, so my domain of my function is those 3 intervals there. Okay. Any questions on the domain? All right, now the domain is kind of important, but it doesn't really tell us what the graph looks like. So another thing that we might want to know about is the x and y intercepts, right? Okay, so I know we haven't in this class gone over like what the x and y intercepts are or how to find them. You forgot your keys. You're welcome. All right, but we can figure out what the x and y intercepts are. Also, I think, yep, they're good. Okay, so going back to Math 140 or our algebra classes or pre-calculus classes, does anyone remember how to find an x-intercept?
Set x, or wait, x-intercept. Set y equal to 0.
Set y equal to 0, right? And I know it's very counterintuitive. It seems like to find the x-intercept, you would plug in x equals 0, but it's actually the opposite, right? We're finding where the graph touches the x-axis, which is actually where y is 0. So we're plugging in y equals 0. Okay, so let's see. Y is on the left side, and then the rest of it stays the same. So it's 2x squared over x squared minus 1. Okay, how do I solve an equation where like there's a denominator and it's set equal to 0?
Just multiply by the denominator on both sides.
Multiply by the denominator on both sides. So x squared minus 1, x squared minus 1. Looks like these cancel out, and well, anything times 0 is 0. So it's essentially the numerator being set equal to 0, right? Okay. Well, dividing by 2 on both sides gives me 0 equals x squared, and square rooting both sides gives me that x equals 0. Okay, so my x-intercept is when x equals 0. Now, is an x-intercept just like an x value, or is it a point? It's a point, right? So I also have to figure out what y is at the x-intercept. So let's plug that in. F of 0 is what, 2 times 0 squared over 0 squared minus 1, which is 0. So it looks like my x-intercept is 0 comma 0. Okay. Well, now we have to do our y-intercept. How do I find my y-intercept? Yeah, plug in 0 for x. Okay, well, we already know what that is, but let's just do it. So we got y equals 2 times 0 squared over 0 squared minus 1. We already said that was 0. So our y-intercept is also, well, 0 comma 0, right? Okay. All right. Any questions so far? All right, I was kind of stupid plugging in 0 at the end of the x-intercept, but that's fine. Okay, let's move on. We figure out our x and y intercepts, and we know the domain of our function. So that's some information that we can use to graph a function. Let's talk about some other stuff that we've been doing. Okay. Vertical asymptotes, right? Remember, vertical asymptotes are those like straight lines that the graph kind of gets close to, but like never touches it, even though, okay, we can touch it, but don't worry about that. All right, does anyone remember how we like defined a vertical asymptote way back when we talked about limits?
Was it in the place where the function doesn't exist?
It is a place where the function doesn't exist. There's actually a more technical definition in calc. Yeah, a vertical asymptote is any place where the limit of a function, so as x goes to a from either like the right or the left, yeah, equals infinity, right? So this is what we're looking for. But I'm kind of lazy. I really don't feel like doing it. We already know what the domain is. So why don't we just say the vertical asymptotes are where we don't exist? So kind of what Sam said, x equals -1 and x equals 1. Okay. Let's not worry too much about the limit definition because, well, we kind of already know what they're going to be. All right. Let's keep going. All right. Apple products on the floor. Let's do the horizontal asymptotes. Does anyone remember the limit definition of the horizontal asymptote? Okay, but what's the definition? Does have to do with the limit.
Where y approaches infinity.
Not as y approaches infinity, but as x approaches infinity. Yeah. So there's only 2 possible horizontal asymptotes. It's the limit as x approaches infinity of my function, or the limit as x approaches negative infinity of my function. Okay, so these are actually things that we can solve. And let's go ahead and do it. Okay, let's do the limit as x approaches infinity first. So this is 2x squared over x squared minus 1. Okay. Anyone remember how to do this?
The same, if they have the same power, then you should divide the coefficients.
Good. So the one on top has degree or the highest power of 2 because the x is squared. The bottom has a degree of 2 because the x is also squared. So since they match, we just take the coefficients of the highest powers. So I know that the coefficient of x squared up top is 2. The coefficient of x squared on the bottom is 1. So this limit is 2. Okay. Now we also have to do the limit as we go to negative infinity. I think I told you didn't have to know how to do it, but let's just go over how we do it really quick. You don't have to know how to do this, but 2x squared over x squared minus 1. It's literally the same thing, but you just have to think about the sign. Since the x is squared, we're always going to have positive values. So this is also just going to be 2. Okay. I'm going to make a note here. Don't worry about the limit as we go to negative infinity of polynomials. I think it's a little bit more conceptual, but just know that it's 2. Okay. So I know that I have a horizontal asymptote, right? And I know it's going to be the horizontal line y equals 2, right? So I know that this is my horizontal asymptote. Okay. Let's go to part E here. Part E says draw a preliminary sketch of the function. So let's just put everything that we know so far and try to see what the function looks like. Okay. So when we graph a function, usually we do an X and Y axis, right? That's usually kind of how we go about things. So let's do that. Okay. Let's take a look at what we've done so far. We know that the domain says that the function doesn't exist at x equals -1 and x equals 1, right? So maybe I should draw that. Okay. I also know that at -1 and 1, we have a vertical asymptote, right? We said that on part C. So let me draw some vertical asymptotes. Okay. All right, that's basically all I know about -1 and 1. And taking a look at part B, we have an x-intercept at 0, 0. So I know that the function has a point here, right? I know that that value does exist, okay? And I also know that there's a horizontal asymptote at y equals 2. So at 1, 2, I know that there's an asymptote here. That's very badly drawn, but I think you get the point here. Okay. So I know that this isn't like a very nice drawing of the graph because we don't really have the graph on here, but I do know that my graph is going to do this. It's going to be in these sections. I know that there's a point here, so it's probably going to do something around here, right? And I know that I have my asymptotes. Okay, so we have that information. Any questions so far? All right. Let's go and answer some more questions about our graph. Okay. Well, part F and part G tells us to find the first and second derivative. Why don't I ask you to take some time and find these derivatives? What rule are we using? Quotient rule, right? I see some good work, and I do want to end this class not right at the end point, just because I feel like it's Thanksgiving. We don't feel like staying here for a while. So let's just go over this one real quick. The quotient rule tells us that F has to be on top, G has to be on the bottom, right? And I know that the derivative of any quotient is the bottom G times the derivative of the top minus the top multiplied by the derivative of the bottom over G squared, right? All right, well, that's pretty easy. I know that the bottom is x squared minus 1. The derivative of the top is 4x, right? I'm subtracting off the top 2x squared times the derivative of the bottom, which is 2x. And I'm putting this all over x squared minus 1 squared. Okay. Now this would be fine for a derivative. Like if I asked you what the derivative is, I would mark this correct, but it's not very helpful to us when we're like trying to figure out like things and things later on in the questions that I'm asking you later about like concavity and things like that. So why don't we just kind of simplify this a little bit more so it's easier for us in the future, okay? So what I'm gonna do is I'm gonna take my 4x and multiply it over to the x squared and the -1. So that's gonna give me 4x cubed minus 4x, okay? Then I'm going to take my -2x squared and I'm going to multiply that by the 2x, okay? So I'm going to subtract off 4x cubed and put this all over x squared minus 1 squared. Okay, so what I'm left with is it looks like these guys cancel and my derivative is -4x over x squared minus 1 squared. Okay, did everyone get that for their first derivative? Okay, I think everyone's pretty good here. Now, the second derivative, also the quotient rule, we want a top and a bottom here. Now the quotient rule tells us that we have to take the derivative of the bottom somewhere in there, right? So before we apply the quotient rule in part G, let's just figure out what the derivative of x squared minus 1 squared is first, okay? And then we'll go ahead and do the quotient rule, okay? What rule am I going to use to figure out the derivative of x squared minus 1 squared? Chain rule, good. So what's the inside function? Good. And I guess that makes the outside function something squared, right? Okay. So the derivative of the outside is going to be 2 times something to the first power. The derivative of the inside is 2 times x minus 0. And once I'm done doing that, I can just stick the inside back in the box. X squared minus 1. Okay, so essentially the derivative of the bottom, sorry, David, is 4x x squared minus 1. Oh, it gets worse. We're not even down to the writing. It gets worse. Okay, so all I've done is found the derivative of the bottom, so we don't have to think about it when we do the quotient rule again. All right, let's do quotient rule again. It's telling us to do g times f prime minus f g prime over g squared. Okay, so let's just plug in. I know that g, or my bottom, is x minus 1 squared. Oh, x squared minus 1 squared, sorry. I'm going to multiply that by f prime, which I think is -4. I'm subtracting off f, which is -4x, times g prime, which is what we found right there using the chain rule, 4x times x squared minus 1. Okay. And on the bottom, we have g squared. Okay. What is the square of x squared minus 1 squared? Yeah, right. So when I square something, I just multiply the exponent by 2. So this is the x squared minus 1 to the 4th power. Okay. Now, normally, when I ask you to use the quotient rule, you really don't have to simplify it. But because I'm going to ask you questions about concavity, points of inflection, things that involve the second derivative, it might be really useful for us to simplify this so we don't have to think about how to solve equations that look really funky later on, okay? So I know it's very tempting to FOIL things out, right? Whenever we see something squared, the first thing we want to do is FOIL, right? I'm going to tell you that foiling might not be the best option for us here because we have things that kind of match on the top and bottom. Like we have an x squared minus 1 and an x squared minus 1 there. So because of that, I'm not actually going to FOIL it out because maybe we have a chance to kind of cancel things out later on, okay? So what I'm going to do first is just clean everything up so it looks a little bit nicer, okay? So let me multiply the -4 out front. So it's -4 x squared minus 1 squared. Foiling, or not foiling, multiplying things out here, it looks like the negative turns into a positive, and we have 16x squared times x squared minus 1, and the bottom just stays the same. Okay, so does everyone kind of see how I got to that step here? Okay. Now, instead of foiling things out here, does anyone see something I can do to like factor something out? Good, right? So what John said is, look, there's an x squared minus 1 here, and there's an x squared minus 1 there. So instead of like foiling things out, I'm actually going to do the opposite. I'm going to factor out an x squared minus 1 because everything does seem to have that, okay? Everything also seems to have a 4 and a 4 there. So why don't I factor out, actually, I actually don't feel like factoring out the 4. Let's just factor out the x squared minus 1 to keep it simple. Okay, let's just factor out an x squared minus 1 in the numerator. Okay, Now, what we'd have left is a -4. The x squared minus 1 squared just turns into x squared minus 1 because I took away the 2 factor. And the 16x squared takes away that x squared minus 1, so we just have 16x squared up top. Okay. So does everyone kind of see how I FOILed out or factored out an x squared minus 1? Good. What can we do to simplify now?
The denominator and x squared minus 1 to the power 3, get rid of the x squared minus 1 up top.
Good, right? These both have x squared minus 1, so I can just cross out this x squared minus 1. If I do that, I have to replace the 4 with a 3. Okay, so what I'm left with up top is -4 x squared minus 1 plus 16x squared. And what I'm left on the bottom is x squared minus 1 cubed. Okay, now that I'm here, I can't really factor anything out anymore. So at this point, I'm going to start multiplying through. Okay, so I'm going to multiply the -4 by the x squared to get -4 x squared plus 4 plus 16x squared. And on the bottom, I'm going to have x squared minus 1 cubed, not touching it. What else can I do to simplify this?
Like terms, so
Yeah, we got some like terms here. We have a -4x squared and a 16x squared. So let's combine those. And I think we'll be left with a 12x squared plus 4 over x squared minus 1 cubed. Okay. Now I know you might want to factor out the 4. You can do that, but I'm being lazy. So I'm just going to leave it like this. This is my second derivative. All right. Any questions on finding the first or second derivatives here? All right, I think it's pretty good review to do the quotient rule twice. Let's keep going. Okay. So let's flip over to part H. All right. Part H, finding critical numbers. How do I find critical numbers? Good. Set the first derivative equal to 0. What else do I have to look for? Where the first derivative doesn't exist, but the function exists, right? Okay, so let's just make a little note. Critical numbers are where the derivative equals 0. Also where the derivative doesn't exist, but there is a caveat that the function has to exist also, okay? All right, let's do the first part. Let's set f prime equal to 0. Okay, well, it's really nice that in part F we found the first derivative. So why don't I just set -4x squared over, gosh, oh, it's 4x, isn't it? Okay, there we go. 4x over x squared minus 1 squared equal to 0. Okay, remember, whenever we set a fraction equal to 0, essentially what we're doing is setting the numerator equal to 0. So I'm just going to ignore the denominator and set that equal to 0. Dividing by -4, we get that x equals 0. Okay, so x equals 0 is a potential critical number. Let's also find out where our derivative doesn't exist. How do I find where my derivative doesn't exist?
so to the denominator, set 0 equal to the denominator.
Yeah, this is where we set the denominator of the derivative equal to 0. So x squared minus 1 squared equals 0. Okay. I know this looks really crazy to solve, but basically we have a square. Let's just undo it by taking the square root of both sides. Okay. We're left with x squared minus 1 equals 0. Okay. Adding 1 to both sides gives me x squared equals 1. And taking the square root of both sides, I have plus or minus 1. Okay, so we have 3 potential critical numbers here: 0, +1, or -1. Okay, now there is a caveat here. Just because I found the x values where my function equals 0 and where it doesn't exist, that doesn't mean that they're critical numbers. I have to go back and plug them into my function to figure out if they actually are in the domain, right? Yeah, actually, we know the domain of F, right? Well, we actually know all of them technically by knowing the domain. So let's actually skip plugging in the function. The domain says F or X can't be -1 or 1. Those are the only things that don't work. So Jude was actually pretty smart here. You don't actually have to plug in to figure out if it's in the domain. I already know that -1 and +1 aren't in the domain of my function. 0 is. So my only critical number here are, well, just 0. Okay. Any question on part H? Okay, so just because the function doesn't exist at x equals -1, that doesn't mean that it's a critical value. That value is kind of important, but not because of the reasons that we think. Okay, let's go on to part I now. All right. Part I is going to tell us where our function's increasing and decreasing. Now you can kind of tell this is really important when we're drawing the graph because, well, when we draw it, we want to know if we're going to go up or if we're going to go down. So let's go ahead and do this, okay? Remember, when we're doing intervals of increase and decrease, we set up our number line, right? So we kind of set up a number line. And on this number line, we're going to put the critical numbers. And we're also going to put the places where our function doesn't exist, right? Because, well, if our function doesn't exist, we're not actually increasing or decreasing at that point, right? So I'm going to put 0 on here. I'm also going to put -1 and +1 on here, okay? Because, well, those are interesting points of my function. All right, let's start plugging in values. Okay, so what's the number below -1? -2, that's what I like to hear. All right, and what am I plugging -2 into? First derivative, right? To find intervals of increase and decrease, we're plugging things into f prime because that tells us if we're increasing or decrease, right? So we're plugging it into f prime of x. Okay. Now I know that f prime of x is -4x over x squared minus 1 squared. Since I have something squared in the denominator, I know that the denominator is going to be positive, right? So I know that this is going to be positive. It kind of just matters what the top is, right? All right, so if I plug in -2, I'm going to get -4 times -2 is 8 over something positive. So that means, well, I have something positive below -1, okay? Which means I'm going to be increasing here.
That's circle plus.
It just means it's positive. So I don't care what the number is. I just care if it's positive or negative. Mhm. All right, what's a good number between 0 and -1? Yeah, -0.5 is pretty good. Still plugging it into my derivative. The bottom is going to be positive. -0.5 times -4 is +2. So this is going to be something positive. So we're also increasing here. Okay. I guess you can tell that I'm going to plug in +0.5 between 0 and 1, right? -4 times +0.5 is -2 over something positive. Oh, looks like I'm negative here, so decreasing. And then finally, I can plug in x equals +2, which would give me, -8 over something positive, which is also negative, so we're decreasing here. All right, so we found our intervals of increase and decrease, but I want to represent this in interval notation because, well, that's kind of how we do things in math. And I know it's a little bit tricky when we do this. So can anyone tell me the intervals of increase and decrease? Or how about increase first? So where are we increasing here in interval notation?
-8 to -1.
Good. Okay, remember, at the point where the function doesn't exist, we're not increasing or decreasing. So we do have to split up the intervals of increase here, okay? Now, am I using parentheses or brackets for the numbers? parentheses, right? Because at -1, we aren't increasing or decreasing. Okay, I'm going to use that U symbol that just represents union between two things. You don't really have to know it, but I like doing it because it looks nice. All right, and then the decrease is going to be the same thing, but opposite signs, right? So we got 0 to 1 and 1 to infinity. Okay. So I know that my function is doing some sort of increasing thing below 0, and it's doing some sort of decreasing 0 after 0. Okay. All right, any questions so far? I know this is a lot of writing, but we'll get there. All right. Next, let's find some local maxes and local mins. Okay, I know that I'm increasing over here, which means, well, I'm not really having a local max or min around -1. I know I'm decreasing at +1, no local max or min here. At 0, am I having a local max or a local min? Local max, right? Because we go from increasing to decreasing. Okay, this is technically doing the first derivative test, right? So I know that there is a local max.
It's 0, 0, 'cause we already plugged in 0.
Yeah, we did already plug in 0, didn't we? So a local max happens at 0, 0. Okay. I know it's 0 because, well, you plugged it in. Okay. There's no local mins, right? We didn't find any. All right, so we know local max, we know that there's no local mins, we know where we're increasing and decreasing. Let's find out some other things about this function. All right, let's find all the x values where the second derivative is 0 or doesn't exist. Oh, it was 0, 0. Okay. Mhm. All right, well, let's take our second derivative and figure out where it's equal to 0. Now, remember, whenever we take a fraction and set it equal to 0, we're essentially taking the numerator and setting that equal to 0, right? So numerator equals 0. Taking a peek at my second derivative, the numerator was 12x squared plus 4. So 12x squared plus 4 equals 0. I can subtract a 4 on both sides. So I have 12x squared equals -4. Dividing by 12 gives me x squared equals -1/3. And I can take the square root of both sides. What's the square root of -1/3?
It's imaginary.
It's imaginary, right? Or it doesn't exist in our case. Whenever we do calculus, unless we want to breach into this thing called complex analysis, we don't deal with imaginary numbers. So there's actually none or no places where f prime of x equals 0. Okay. Let's find places where our second derivative doesn't exist. Okay. Remember, this is essentially setting the denominator equal to 0. My denominator is x squared minus 1 cubed. Okay. We can take the cube root of both sides. That usually works. But since we have a 0, it doesn't really matter. We're left with x squared minus 1 equals 0. Yeah, that looks familiar, doesn't it? Add 1 to both sides, x squared equals 1, x equals plus or minus 1. Okay, so we have two places where our second derivative doesn't exist, right? We got -1, and we got +1. All right, let's keep going. Part L, right? L is asking us the intervals of concave up and concave down. So let's go ahead and do that. Remember, when we do intervals of concavity, we set up the number line again. I know. And we like to put in places where our second derivative doesn't exist here, right? Because that can be important. We can jump from concave up to concave down where our second derivative, well, doesn't exist. So I'm going to put -1 and 1, what we found in part, gosh, I'm not good at this alphabet, part K on here. Okay. So a good number below -1 is -2, right? what am I gonna plug -2 into? Second derivative, right? The second derivative is the function that tells us if we're concave up versus concave down. So I'm gonna plug it into f double prime of x. Remember, that was 12x squared plus 4 over x squared minus 1 cubed. Okay. Plugging in -2, 12 times, oh gosh, that's 12 times 4 plus 4. -2 squared is -4 minus 1 cubed. Do you think that's going to be a negative or a positive number? Oh, wait. Nope, that should be +1 minus 1. +4 minus 1. Think this is going to be a positive or negative number here?
Positive.
Positive, good. If we get a positive number, does that mean we're concave up or down? Up, concave up. All right. I think a good number in between -1 and 1 is 0, right? 0 is usually a good number to plug in. Okay. So we got 12 times 0, which is 0, plus 4 over 0 minus 1 cubed. That's going to be a negative number, right? Which means we're concave down. Okay. And then plugging in x equals 2 gives us 12 times 2 squared, which I think is like 48 plus 4 over 2 squared, 4 minus 1 cubed. That's going to be a positive number, so we're concave up here. Okay. So our intervals of concave up are -infinity to -1 and 1 to infinity. Concave down is between -1 and 1. Yeah, I think we can figure out what this function looks like right now. Okay, what are my points of inflection? David?
Just figure out what CD and CD meant.
Oh, yeah, concave up and concave down.
Would there not be any points of inflection because it's not, there's no change from a max to a min?
Oh, it's not max to min,
It's
Or
changed.
increasing or decreasing?
not increasing, decreasing. Inflection points
Or
are,
or inflection points.
yeah, concave up to concave down, right? That's what we're looking for. But you are right that there aren't any inflection points.
We know it doesn't exist where it
Yeah.
switches.
Yeah, right. So technically we do change from concave up to concave down at -1, but an inflection point is a point on the graph. Is -1 a value where my graph exists?
No.
No, right? So even though we do switch, from concave up to concave down, oh gosh, at x equals -1 and 1. At these points, my function doesn't exist, so there's no inflection points, okay? Okay, so I know it's very tempting to be like, oh, there's an inflection point at -1 and 1. My function doesn't exist, so if I try to plug it in, nothing would happen. It's not in the domain of the function. No inflection points here. All right. Any questions before we put this all together? All right. So we did all this work to figure out what this function looks like. Let's just write out what we have so far. You don't have to write this. I'm just going to do this to kind of look at what we've done. In one of our parts, we found out that the intervals of increase are between -infinity and -1. We also know that we're increasing between -1 and 0, right? Is that what we said? Yeah. And decreasing between 0, 1 and 1 infinity, right? So those were points where we increased or decreased. We know that there's no local min, okay? The local max we said was 0, 0, okay? Our intervals of concave down were -1 to 1, and the intervals of concave up were the other points, -infinity to -1 and 1 to infinity. We also realized that there were no inflection points, okay? So let's figure out what this graph looks like based on all this information. And what I'm going to do is, I know some of you don't have an iPad, but I'm going to kind of cheat here. I'm going to take our preliminary sketch of our function and just kind of copy it on here. So if you don't mind copying what you got for part E on the last page of our notes here. And this is the preliminary sketch of our function, right? Didn't look very good, but it did give us some information as to what our graph looked like. Okay. Let's kind of label what we have so far, okay? I know that between negative infinity and negative 1 and negative 1 to 0, so everything here we have increasing, right? Everything here we have decreasing. Okay, so that's what the increasing, decreasing told us, okay? I also know that there's a local max at 0, 0. We also know that intervals of concave down are between -1 and 1. So here we have concave down, and all the rest are concave up. Okay. So let's think about this. Let's just start on the left side of the -1 vertical asymptote, okay? So let's just figure out what's going on over here, okay? If we are increasing and concave up, do you think I'm gonna be below the horizontal asymptote or above the horizontal asymptote? Above it, right? Because concave up means it's shaped like a cup. It has to increase. And if I have a horizontal asymptote here, it's going to increase like past the horizontal asymptote, which is probably what I don't want here. Okay. So I know my function's going to be above the horizontal asymptote. I know it's going to be increasing and it has to follow the asymptotes. So my function's going to look somewhat like this on the left side. Okay. Now, in the middle, I know my function has to be here because I have a point. I know it's going to be a local max, so I have to be kind of like a peak here. And I know I have to adhere to my my vertical asymptotes here. So I know I have to kind of get closer and closer to these asymptotes. So I know my function has to look like this over here. Finally, on the right-hand side of my graph, I'm concave up and decreasing, which means I need to be going down here. Okay. So using my information about concave up and increasing, decreasing, I know my graph has to look like this on the right-hand side. And well, there we have it. Our function looks like this. I know we could have easily plugged it into our graphing calculator and done it, or plugged it into a computer. Does it look like the graph? Yes, we did it. And this is why this section is kind of useless, but we do have to cover it because we have some old people in the department that say we have to do it. So, all right, any questions? All right, then I hope you have a great Thanksgiving break. We have done it. We have finished all the classes before Thanksgiving break. Yeah. All right.
Have a nice Thanksgiving break.
Oh, thanks. That was